the cloud and let's share the screen. Okay, last class we looked at Mohr circle, and we were looking at worksheet number 12, and we solved one of the problem. So if I go back, so if you remember my, this is the solution actually. The one we did last class is this one. And my, as I have mentioned, my circle was very bad. So I just wanted to show you guys how if you draw the circle, it's not a perfect circle because I didn't use a compass, but the circle will look something like this. And you can see that the y prime is somewhere here. So you should know. Okay, so if you draw it properly, this is how it should look like. Okay, so we left off somewhere. We finished this, but we didn't finish. We did not actually calculate the principal stresses and directions, did we? Let me see. No, we did not calculate that. We only calculated the what is going to be the sigma x prime, sigma y prime. So this was the stresses at x, y prime. So today we're going to look at how to get the principal stresses and their directions from the Mohr circle and the maximum shear stress. Okay. So I'm going to go back to this one. I'm going to use this circle because this is more, this looks better. So if you can see, this is your sigma axis, and this is your shear stress axis. Okay, so where the points where your shear stresses are 0, that's where you're going to see your principal stresses. So this is maximum principal stress, so I named it as sigma 1, and this is minimum principal stress, so I named it as sigma 2. Okay, and remember this is your x phase, this is your y phase from last class. Okay, so how much is my sigma 1? Well, sigma 1 would be, if you recall, this is the center of your circle. So from here all the way to sigma 1 is the radius of your circle. Okay, and you know the value from origin to the center of the circle. So your sigma 1 is basically your this value. So it's going to be total radius minus 8. 8 is from here. I should use a different color. So 8 is going to be from here to here, whereas this is the radius, and this is 8. Okay, and the units are in KSI, so I should put the units KSI for both of them. You should always put units beside the axis label. Okay, so radius minus 8, so sigma bar is actually the distance from the origin to your sigma bar is actually your sigma x plus sigma y divided by 2. Okay, so in this case it is 8 from here to here. So this is the formula. So you have 10, this radius minus this will give you, what is this value here? So 2 KSI. And let's look at sigma 2. So remember, I put plus sign because your sigma bar is negative 8. So this sigma bar is, so sigma bar, if you look at it, is sigma x plus sigma y divided by 2. Okay, so your values were, so it should be, you can see your sigma x is -8, sigma y is -8. So -8 by 2, that gives me -8 KSI. Okay, so that's why, because it is minus, negative in nature, that's why I put plus here. Ultimately, it will give you this little number. And my sigma 2 would be, okay, so my sigma 2, we know that from here all the way to sigma 2 is your radius. And from here, okay, so sigma bar is your center. All right. So, so you want to know what is the value up here. And from all the way from here to here, where your sigma bar is, at the which is the center of your circle, is -8. Okay, so you just have to add the values. So since this is negative, this is actually -8. What happened here? -8. So from here to here is the radius. So I'm actually, your sigma bar is -8, and minus this radius value will give you the total value all the way from the origin to where you have your sigma 2. Okay, this is what I wanted. So -8 minus r. So sigma bar is -8 and r is 10. So it gives you -18 KSI. So your sigma 2 is -18, sigma 1 is 2 KSI. Now let's look at the angle. The angle is always you're gonna measure the angle from the x phase. So where is my x phase? Here is my x phase. So if I go actually to sigma 1, where you have your sigma 1, so if I go from here all the way to sigma 1, that angle is, I'm going what? Clockwise. So this is a -90-degree angle. And remember, on Morse circle, your angle is always twice. So the actual angle, theta 1, is going to be -90 divided by 2, which is -45. Okay, and it is clockwise. That's why you have this negative sign. All right, let's look at theta 2. Theta 2, the angle is always measured from the x phase again. So you're gonna go counterclockwise all the way to sigma 2. That will give you theta 2. Now this is going counterclockwise. So so it's going to be a positive 90-degree angle. And again, on Morse circle, the angle is always twice. So you have to divide it by 2 here. And this gives you positive 45-degree. Okay, now let's look at, so we looked at how to get principal stresses and directions from your Morse circle. Now we're going to look at how to get the maximum shear stress and direction from the given state of stress. The given state of stress is your XY faces. So maximum shear stress is the radius of your, it is actually the radius of your Morse circle. So tau max is always the radius. And you can see that the maximum shear stress, you're going to look at it in the y-axis. So the max y-axis value is 10 plus minus 10, max mean. So these are the locations where you're going to see maximum or a minimum shear stress. So you can see that my maximum minimum shear stress is plus minus 10 KSI. Okay, and how much is the shear? So if you look carefully, so for the x-axis, so this is the point where you see maximum shear stress. The x phase surface, the x phase by itself tells me that. Okay, now because this is shear stress, so you're seeing positive 10 degree, but 10 KSI in reality is actually negative 10 KSI, and the angle from this x phase to this phase is actually 0. So for negative 10 KSI, your shear stress angle is 0 degree. And for positive, and for the positive maximum shear stress, which you're going to see on the Y face, so that is going to be, you're going 180 degree. So if you go 180 degree, that's twice the angle. So the actual angle is 90 degree, 180 divided by 2. So that will be for the positive shear stress. That's that. So positive 90 degree, that angle is for the positive maximum shear stress, in plane shear stress that you see. And theta 0 is for the negative in maximum in plane shear stress you see. All right. So this concludes the end of problem 8.52. And I'm going to move to the next one. We have two problems actually here. The next one is on problem 8.60 from your textbook. So before I move to that, do you guys have any question regarding the last problem? So I have someone here in the chat. Too long. Amir, what do you mean by too long?
Yes, the question is like you have to do so much stuff.
This is the easiest one.
Yeah, I mean, I didn't get it right because I'm also using my iPad, and to do the circle, like I got lost with the dimension of all the dimension that we had to take, because I don't have proper circle too.
So I think the best way is, I think somebody mentioned not to take too long. If you look at my circle, it's too big. So it's better, I should have taken it as, you know, go to each side, the axis. I shouldn't have started 0, 1, 2, 3, 4, 5. I should have started 0, 2, 4, 6. So if
Yeah, okay, I see.
you get a smaller circle.
Mm-hmm.
And then the other thing is, remember, whatever axis you choose for your sigma axis,
Mm-hmm.
you choose the same for your tau. Otherwise, you're not going to get a circle even. So you cannot go like 0, 2, 4, 6 in your x-axis and 0, 1, 2, 3, 4 in your y-axis.
Yeah. You want to keep it the same. Yeah.
Yes. Yes. And yeah, and if you guys have access to compass, that's easier. You can draw it much easily. Other than that, do you guys have any other question, people, in terms of understanding just what we did? Everybody is awfully quiet.
Professor, did you ask something?
I'm good.
Yeah, everything's good. Let's move to the next one.
Okay. All right. So, I know some of you are thinking, oh, this is too long, but you'll see most of the problems here, you will be asked to either to draw a Mohr circle, or the Mohr circle will be given to you. And all you have to do is identify the X and Y faces on your Mohr circle, identify the X prime, Y prime faces on your Mohr circle, and be able to calculate the stresses. I mean, this is one of the easiest problems that you're going to be seeing. Now let's look at this. Use the Mohr circle to determine the followings for the state of stress shown. Show the results on properly oriented elements. So you have, the question asks you, hey, for this problem, what is the principal stress? What is the maximum in plane shear stress? So it doesn't ask you for any, it doesn't give you any angle and asks you, hey, what are the stresses about those along the axis, about in that angle. It doesn't ask you, just straight away asks you what are the principal stresses and maximum in plane shear stress. So let's look at this problem. So obviously, how much is your sigma x? So your sigma x is this, and it is a compressive stress. So your sigma x is equal to minus 6 ksi. Now let's look at the other one, sigma y. The first thing in this problem, Mohr circle or stress transformation, the first thing you should do is list out how much is sigma x, how much is sigma y, how much is tau xy. So you can see that your sigma y, which is this, is also compressive, so it will be a negative stress. And this one is your shear stress. Now, which one is my positive X face? This is my positive X face. And in which direction is my shear stress directed? In the negative Y direction. So this must be a negative shear stress. Okay, so now we are going to calculate. We have to draw the Morse circle. Remember, it tells you use Morse circle. Alternatively, you could have used the equation. You know, there are equations for sigma 1, sigma 2. We did it in our last worksheet. So you could also use that formula, but if it mentions that, hey, you have to use Morse circle, then you have to draw the Morse circle. So let's draw the Morse circle here. So I'm going to try and make it as perfect as possible this time. So we have 0, these are all negative. I'm sorry, I did not put negative. Okay, so this is my tau axis in KSI, and this is my sigma axis in KSI. So now I'm going to actually draw it. So I'm just for checking, I will actually calculate the center of my circle, sigma bar, which is sigma x plus sigma y divided by 2. So sigma bar turns out to be -6 minus 18 over 2. That gives me around -12. So this will help you with your Morse circle sketching, because you now know this is the center of your circle. But right now I'm going to now identify this, draw my Y face. So for my Y face, the coordinate is going to be, so for Y face, the coordinate is going to be -18 -4. That's the coordinate, because shear stress sign does not flip for the Y face. So let's do this. -18 and -4. So -4 is somewhere here. Oh, minus. I am sorry, I did not. So we have to draw this. -2, -4, -6, -8. Okay. So now I'm going to -4, -18. So this is my Y face. I'm going to draw my X face now. X face coordinate is going to be -6. Now the shear stress sign will be flipped. It is actually negative, but for your X face is going to be positive. So I have -6 and +4. Something like this. And if I draw a line through them, it should pass through. So this time, let me just. Okay, so this is going to be, this line should pass through the center, which is sigma bar, -12, okay? Now, if you have access to some compass, then you can put the compass here, take this to be your radius, and easily draw a nice circle. Right now, I cannot do that, so I'm just going to draw an arbitrary circle.
So close.
It was close. It was getting close. I just don't want to draw something. Something like this, the circle. So you're gonna get something like this. Now, where is your sigma 1 and sigma 2? Okay, so this is my X space. So my sigma 1, sigma 2 is going to be, so obviously, this is my sigma 2. This is going to be my sigma 1, okay? And I need to know what is this angle. This will give me my 2 beta 1. If you go from X space to sigma 1, you're gonna get twice the angle of, twice the direction for the sigma 1, which is theta 1, okay? So let's calculate sigma 1. So you all know what is the distance from here to sigma 1. That is the radius, right? That is the radius of your circle. And this is sigma bar all the way from here to the origin. This will give you sigma bar. So your sigma 1 will be, okay, so we have to subtract, right? And it's going to be we can see that it's going to be a negative number. So definitely we're going to put sigma bar plus sigma bar plus r. So we need to know the r radius. So let's calculate the radius, people. So you can easily calculate the radius. So if you draw it to scale, so you can actually measure it, okay? But the radius of the circle, let's first calculate the radius. So your radius would be, okay, so this is your shear stress. So remember, you can calculate it this way. This distance is how much? 4. And this, for the radius, we do not need any sign convention. So if you consider this triangle, the distance from here all the way here is, this is r. This distance is 6, right? So if I know, so I'm considering this this triangle. This will give, the hypotenuse will give me the radius. So it's going to be 4 square plus 6 square root over. So that gives me root over 52 KSI. That is my radius. So if I want to know my sigma 1, my sigma 1 is going to be minus sigma bar plus r. Sorry, sigma bar plus r actually. Sigma bar plus r. So sigma bar is negative 12, that's the center, for all the way from the origin to the center of the circle, plus the radius. Radius is how much? 50 root over 52. And it gives me something like negative 4.79 KSI. Okay. So I think this should have been somewhere slightly here. But anyway, it's not a perfect circle. That's why we don't have it. All right. Let's go to sigma 2. For sigma 2, obviously, this is your radius all the way from here to your sigma 2. That's the radius, right? So for sigma 2, it's going to be sigma bar minus r, because we have to add this sigma bar to this r to get that coordinate for sigma 2. So we're looking for the coordinate number. So sigma bar is negative 12 and your r is negative, 52. That gives me negative 19.2 KSI. So these are my principal stresses. I also, whenever you mention principal stresses, you were also asked to show your results on a properly oriented element. So for an element, you need the directions as well. So we need this 2 theta 1. And where is your theta 2? Your theta 2 will be from x phase all the way to sigma 2. So that is, this is your theta 2, twice of theta 2. So for now, I just need one angle. So 2 theta 1 would be, so you can easily calculate theta 1 using this triangle, opposite by adjacent. So tan of 2 theta 1 is equal to, okay, so I'm going to say tan inverse. Let's just write, and this theta will be a negative angle. Why? That's because it's going clockwise. Clockwise is always negative. So opposite is 4 and adjacent is 6. So I'm going to write, hey, 4 by 6. So my theta 1 turns out to be negative 16.8 degree. Okay, that's the direction, that is the angle between this given x phase and sigma 1. That's the angle between them. Now let's calculate 2 theta 2. So 2 theta 2 would be, if you calculate this angle, considering this triangle, considering this triangle.
Sorry, I have a question. Why did you say the angle was negative?
Oh, we are going counterclockwise, sorry, clockwise here. From x phase to sigma 1, you're going clockwise. That's why the angle has to be negative.
Okay, thank you.
I need a unknown. Okay, here. I'm sorry, at that time I did not write it down. Okay, this is the triangle I'm interested in. So for this triangle, if you know this angle, so 180 minus this angle will give you 2 theta 2. So my 2 theta 2 is going to be, now this is going to be a positive angle because you're going counterclockwise from the x phase. So it's a positive angle. So 180 degree minus tan inverse of this angle, So that is going to be opposite by adjacent. Your opposite is how much? 4. We're just taking the magnitude here. And your adjacent is 18. Sorry, not 18, 6. I'm sorry. 6 from here to here is 6. 12 minus 18 is 6. So it's going to be, opposite is 4 divided by 6. So that gives me, if you calculate, your theta 2 is positive 73.2 degrees. So now I'm going to draw this orientation. Most of the time students make this mistake. They don't know how to draw this oriented elements. Okay, so let's draw the elements now. So I'm going to, so this is my x-axis, y-axis. Now I'm going to use the positive angle. It's easier for me. So so if I use the positive angle, then it's going to be from the x phase all the way 73.2 degrees. So something like this. So this is my x prime phase. This is my y prime phase. Now, if you choose theta 2 and draw the angle, and if you choose theta 2 to draw your element, remember theta 2 corresponds to sigma 2. So the stress in the x prime phase, so this angle is 73.2 degrees, okay? And the stress in the x prime phase has to be sigma 2 because the angle you used is for sigma 2, okay? So I'm going to draw it now. So this is my element. So I'm going to draw the stresses. So my X prime face, I have to draw sigma 2 because the angle used is for sigma 2. Use theta 2, so it's negative 19.2. So it's a compressive stress. So it's 19.2 KSI. And my sigma 1 will be 90 degree because they are 90 degree apart. So that is going to be my sigma 1, which is negative 4.79. So I'm going to draw 4.79 KSI. Okay, so that is, let's look at the, will there be any shear, people? Am I missing any stress for this element? People, okay.
Yeah, I think there should be shear.
Okay, Carolina says shear. What about others? Let me see. Christopher Lopez, what do you think? Should there be shear? Am I making a mistake?
Yes.
Yes, okay. Let's
No,
see.
not yes, you are, but I was trying to.
There will be shear. Okay, that's your, okay, Emily. Will there be shear?
I think that there will be shear, yeah.
Okay, who else do I have? Jonathan Ramirez. Will there be shear? Okay, no response. Joshua Corsten. Will there be any shear?
Yeah, that's what I answered. That was me answering before.
Oh, okay. You said it's going to be shear. Okay. The other Joshua. Will there be shear?
I think yes.
Okay. Now let's go back.
Professor, I have a question.
Yeah, go ahead.
When you have a moment. So how did we know the direction of the angle?
Yeah, I can go over it again.
Okay. I'm just a little
All right, so
confused.
how do we
you
know
it's
the
negative.
angles? Angles are always measured from the x faces. So if this is my sigma 1, this is my sigma 1, right? So you're going to go from x face. So this is your x face. So you're gonna go all the way like this to your sigma 1. That means you're going from here to here. So you're going clockwise, and this angle will give you twice the direction for twice the angle between x face and the sigma 1 face, or the face carrying sigma 1. Okay, so if you draw this perfect circle, you can use a protractor to actually measure the angle. You will get it if you draw it to scale. But since I did not draw it to scale, a lot of the time people sketch it. So I am actually using trigonometry to calculate the angle. So if considering this little triangle, so opposite by adjacent, so I wrote 2 theta 1 is equal to minus tan inverse opposite by adjacent 4 by 6. Why minus? Because it was going clockwise. So that gave me an angle of negative 16.8 degree. Now if I want, so this is the angle between x face and the face carrying sigma 1. Now let's look at the angle between x face and the face carrying sigma 2.
So just real quick, I just want to clarify. So you're considering from the x face point to sigma 1.
Yes.
You're saying that is clockwise, and that's why the theta 1 is negative, right?
Correct.
Okay, got it. I think I got it now.
So let's look at sigma 2. So from x face to sigma 2, if you want to go from x face to sigma 2, you have to go what? Counterclockwisely, right? And that angle is your 2 theta 2. So because you're going counterclockwise, it will be a positive angle. So this total angle is 180 degree. 180 minus this little angle will give you 2 theta 2. So that's what I did. So I have 2 theta 2 is equal to 180 minus this little angle. What is this little angle? Opposite by adjacent. My opposite is 4. adjacent is again 6 because 18 minus 12 is 6. So tan inverse 4, so 4 over 6. And if I calculate, it gives me 73.2 degrees. Does that make sense?
Yes.
Caroline? Okay.
Yeah, it does. Thank you.
So I'm going to go back to my definition for principal stresses, since most of you answered that there will be a shear stress. Principal, direction, and stress calculation. Principal, stress, direction. At a specific orientation, the element will have maximum and minimum normal stresses, and the shear stress will be 0 at the principal stress direction. So whenever you have principal stress directions, whether it's theta 1 or theta 2, whichever it is, you do not have any shear stress. Okay, so this is it. So you do not have any shear stress. So I will not have any shear stress here. Whatever I have drawn, these are the only stresses acting in that direction. Okay, everyone? So no shear stress. Now let's look at the next part. The next part is I have to calculate this maximum in-plane shear stress. So the maximum in-plane shear stress is going to be obviously going to be the radius of your circle. So it is going to be, so shear stress is in the y-axis. So you're going to go all the way from here, vertically go up. That will give you the tau max. So that is from the center of the circle all the way to the circumference of the circle. That is the radius. So tau max is plus minus r. So my radius, I calculated it to be 52. Now let's look at the angle. We need the direction because we need to be able to show it in properly oriented elements. So you need the directions. So how do we get the direction? Now the direction is going to be, you're going to go move from again x face to my, so these are my tau max and mean. Okay, tau max and mean. Now this is going to be, so if I move from my x face, just a second. Okay. So so my tau max is plus minus r. So if I go from here to here, so that will give me my twice of the theta s. Okay, so how do I get that angle? So 90 degree, 90 minus this 2 theta 1. So 90, this whole thing is 90. 90 minus 2 theta 1 will give me 2 theta s. So 2 theta s is equal to 2 theta 1. And it is going to be the magnitude, because here I just want to get the magnitude of theta s, okay? And it is going to be positive 2 theta s because you are going counterclockwise. That's why. So how much is the magnitude of my 2 theta 1? It's 16.8 times 2. So 16.8 times 2 gives me 33.6. So my 2 theta is 90 degree minus 33.6, okay? So that gives me around 56.4 degree. My theta s will be half of that. 28.2 degrees. Okay. Now, if I consider this to be my x prime face, then this will be my y prime face. Okay. So if for x prime face, remember my shear stress is always going to be you have to flip the sign. So if this is your x prime face, the shear it's showing positive shear stress. In reality, it's going to be negative. Now, before that, how much is my tau max root over plus minus r plus minus root over 52? That is actually negative 7.21 KSI. So in reality, this little thing almost reads like 8. So it should have been a little down somewhere here. All right, so so let's draw so now I know my tau max. I know my angle. One of the angle is good enough for me. If you know one of the angle, it's good enough for you to draw the it's positive, yeah. So it's a positive angle, means 28.2, maybe something like this. So this is my x, y, x prime, y prime. So if I draw it, so this is going to be my element, and this is 28.2 degrees. So the angle between x and x prime. Now, will there be any normal stress here, people? Will there be any normal stress? Art?
I would say yes.
Yes. Okay, yes, there will be a normal stress. How do you know that? It's because this is the point we are interested in. If you go down, you can read a normal stress, which is same as your center of the circle. So if I clear everything up, so if I clear these things up, so you can see that if you go down, this will read your normal stress, and this is going to read your shear stress for this point. And similarly, in the last time when you were asked to find out this principal stresses, even if you forget that there is no shear stress, you know that this point is your shear stress, principal stresses. So for part A, when you're calculating the normal principal stresses, where is the principal stress? So this is where is your principal stresses are. They are exactly on your x-axis. So definitely their y-axis value is 0. What is in the y-axis? Shear stress. That means in the principal directions, your shear stresses are 0. Your circle is telling you that there is no shear in the principal direction. And also your circle is telling you, hey, at the maximum in-plane shear stress, you do have this to be your normal stress. So my normal stress is negative 12. So negative 12 is going to act in both x, y direction. So I'm going to say, hey, I have negative 12. Oh, this looks like a bad one. This is my y prime face.
Isn't the sign flipped for the x direction?
For the shear stress, not the normal stress. Your normal stress is negative 12. That will remain same. Okay. And here it is reading a shear stress of 7 point, we calculated it, 7.21. And here it is reading negative, although I shouldn't say that this looks not good. Say it should have read somewhere here, up here, you know, negative 7.21 if I've drawn it right. So, but the normal stresses, the sign will not be flipped. The normal stresses will remain same. So it's going to be 12 KSI. I'm not putting the negative sign because you can see it's compressive, so you don't have to. Now in my X prime phase, it is reading positive 7.21, right? So because I'm considering that to be my X prime phase, so the sign will be flipped. So I will have negative shear stress here. So the arrow tells me it will be negative. So 7.21 KSI. And you can draw the rest of it easily. Okay, so this is my stress element for this one. Okay, so if I go back here, I do have a nice solution out here for you guys. So you can see, so this is my maximum in-plane shear stress, where you're gonna see tau max and X prime and Y prime phase. So you can see this is going to be 7.21. This is negative 7.21. Oh, sorry, this is Y prime phase. And you can see the angle. This is 2 theta S, okay? And this is my sigma 1. This is my sigma 2. And you can see that obviously this is your sigma axis. This is your tau axis. And so obviously you can see that where you have your sigma 1 and 2, the tau value is 0. That means there is no shear. Okay. So any questions so far with this problem? I posted some example problem sheet as well as some practice problem sheet. You guys should do some practice on this. It is very important for your final exam. So any question?
Can you go back to the last drawing? I missed something.
This one or the one before?
The one before, for part B, the maximum in plane shear stress.
This is the one?
Yeah, right there. Thank you.
Okay, let me know when you guys are done. So everyone is good?
Yeah, I'm good. Thank you.
No, can I get one more minute?
Yeah, sure. So I would like everybody to actually do practice. You're gonna see, you're definitely going to see one problem on Morse circle. You're definitely going to, I'm going to test you whether you can also calculate these apart from Morse circle, that is using the stress transformation equations. Are you able to do both ways or not? So I'm going to tell you, hey, for Morse circle, use the Morse circle to get this. Or for stress transformation equation, I'm going to say, hey, use the stress transformation equation to calculate the principal stresses and their direction, things like that. Now, a lot of the times I do ask students to recognize the X and Y face and then X prime, Y prime faces and read it from the Morse circle. Maybe I'll give you the Morse circle and I ask you to read from there. So it is important that you practice, okay? Now, is everyone okay? And move to the next part.
Yeah, I'm good. Thank you.
Okay. Are you okay, Amir, or you want me to?
No, I'm good. Thank you.
Okay. All right. So today we are going to start something called the thin cylinder pressure vessel. Okay. So you have a lab with it. You guys do a lab for thin cylinder pressure vessel. And I think there is one lab on, I think there is one lab on Morse circle as well, where you, I think over here in this thin cylinder pressure vessel, you are asked to draw the Morse circle. So this is, both chapters are relevant to this, to that experiment. Now, thin cylinder, thin-walled pressure vessel. So what do I mean by thin-walled pressure vessel? The thick wall thickness is is very, so let me see if I can. Okay. The wall thickness is sufficiently small compared to the radius, okay, of the vessel. So it's going to be, it's a cylindrical vessel or spherical vessel, whatever you have. If your thickness is very, very small, such that the ratio between the radius and the thickness is greater than or equal to 10, then we consider that vessel to be a thin cylinder, thin walled pressure vessel, okay? And you can also consider that the stresses are almost uniform throughout the wall for those vessels, okay? So usually in pressure vessels like that, you're going to have some fluid or some sort of fluid, it can be liquid or gas, inside the pressure vessel. And the fluid is going to exert some pressure on the surface of the inner surface of the vessel, and that will create tensile stresses in the walls of the vessel. So in the experiment, in the lab, I mean, if we were in a different time, you would have done the lab all by yourself, hands-on. I think the pressure inside the vessel is exerted by a pump, which is pumping oil in the pressure vessel, okay, for that particular lab. So basically, whenever you have some fluid inside a vessel, the fluid is going to exert some pressure, and the pressure is going to cause stresses in the walls of the vessel, okay? So if we have a cylindrical pressure vessel, this is, you will see that there is, along the length of this cylinder, so this is the length of the cylinder. So along the length of the cylinder, you're going to see longitudinal stress, which is a normal stress, and along the circumference, in the circumferential direction, you're going to see circumferential or hoop stress. Now you may think that, okay, apart from pressure vessels, where else is it more applicable? Like if you think of the aircraft, you know, the air inside the aircraft is pressurized, right? So, and you can consider the body of the aircraft to be a thin, kind of like a thin cylinder, and you can consider that problem as a thin cylinder problem, because the inside pressure is going to exert stress on the material the whole aircraft body is made of, okay? So this is where it comes handy, and obviously if you have any pressurized fluid for any, if you have any vessel for analysis of those vessels, you're going to be using this. So so if you take a small element from the surface of your pressure vessel, you will see that you have stresses, the longitudinal stresses. These are normal stresses acting along the longitudinal direction, and the hoop stress acting along the circumferential direction. Now the radius is, so all the equation that I'm going to go through is only applicable if you have a thin walled pressure vessel. If it is a thick walled pressure vessel, that means if this ratio is not maintained, then it is considered a thick walled pressure vessel, and which we won't have time to look into in this class, but the equations are going to be different. So these equations are only applicable for thin walled pressure vessel. Now, so let's calculate. So you can see that your longitudinal stress acts perpendicular to the cross section. You can see this is your, so let me draw it somewhere here. I don't want to ruin. Okay, I can ruin it. That's fine. So this is your cross section, and you can see sigma L is perpendicular to this cross section, circular cross section. So that's why it tells me that It acts perpendicular to the cross section. And the formula to calculate this longitudinal stress would be PR divided by 2T, where P is the pressure exerted by the fluid, or okay. R will be is the inner radius. You can see that I have drawn it. So this is the inner circle, and this is the outer circle. And you can see the difference is the thickness T, and the inner radius is considered as R. Okay, so R is the inner radius, T is the thickness of the wall. Okay, so this is how you will calculate the longitudinal stress exerted by the due to the pressure inside the vessel. Now the hoop stress, which is the circumferential stress, it acts along the circumference. So you can see it is in the circumferential direction, goes this way, right? So how do you calculate it? That's equal to PR over T, where P is the pressure, R is the radius, T is the inner radius, and T is the thickness. Now what does it say? Your circumferential stress is twice as large as the longitudinal stress. So a lot of the time, if a pressure cylinder is, if pressure in a cylinder is increased till failure, the vessel will split along this longitudinal direction. Because, why along the longitudinal direction? Because the circumferential stress is higher than the longitudinal direction. So it splits it across this. So it is going to pull this cylinder. Let me draw it somewhere here. If this is your cylinder, so it is going to pull the cylinder this way. So you're going to see that it splits along the longitudinal direction, because sigma C is larger than sigma L, and it is twice as much as sigma L. Okay. If it were to fracture due to sigma L, it would fracture somewhere. So if it were to fracture due to sigma L, so it is going to be pulled this way then. So it will fracture something like this, but this does not happen. A lot of the time you'll see it will fracture this way, because sigma C is high compared to sigma L. Now we looked at, this is the, yes, go ahead. Anybody with any question? Anybody? All right. So this is for cylindrical pressure vessel. You may not have a cylindrical pressure vessel. You may have a thin-walled spherical tank. Sometimes you may have a spherical tank. So in that case, on the surface of the spherical tank, if you take a small element, then obviously you're going to see normal stresses on that element, and you will see that the stresses are all, because it is symmetric. Your cylinder is not symmetric, but sphere is symmetric. Because of symmetry, in different directions, the sphere is indistinguishable, so your stress is constant throughout the vessel. You'll see that the stress is constant, same whether you're going this way or that way, the stress is same, and the stress is PR over 2T. P is the pressure inside that spherical tank, R is the inner radius. So you can see that this is my inner circle, and this is my outer circle. This is my outer circle. And this is my thickness, T, and this is my radius, R. Okay, so Let me just, I think there is some noise coming in. Okay. All right. So, so your R is your inner radius, T is your thickness. Okay. So remember, in all these formula, I used inner radius. The reason being, for a thin cylinder, instead of using a mean radius, you could have used a mean radius, but the formula doesn't use a mean radius because it considers that the difference between inner radius and the mean radius of a thin wall pressure vessel is insignificant. So it just skips it and uses the inner radius directly. Okay. So problems from this chapter, this is a very small part of your chapter 8. At the beginning of chapter 8, you're going to see this thin wall pressure vessel. So I'm going to give you guys some reading assignment, and we're going to look at one problem. Problems based for thin cylinder is very simple. So we're going to look at one problem. So, but basically in your lab, when you do the look at the lab, it has, you guys have studied strain gauges, right? It measures the strain in different direction. So for the lab that you have, so you have this cylinder, okay? And you will see that I think in different directions, you have the strain gauges. So the strain gauges are, I think you have strain gauges in 3 different directions. I don't remember, but I think it's in 3 different directions. So basically, when you have a strain gauge in this direction, it's measuring the strain in this direction. So if you take a small element, okay, so for this particular one, small element is going to be just like this. For this one, if this is the angle, say 30 degree, then you have to rotate it by 30 degree. Say if this is 60 degree for this one, then you have to rotate it 60 degree compared to the red element. So it's going to read, so in different directions, obviously your stresses are going to change. But if you want to calculate the stresses in the longitudinal and circumferential direction, these are the equations that you can use. So you can consider this to be your X direction and your Y direction. And then if you want to know the stresses in different directions, you can, if you know the angle of rotation, you can either use stress transformation equation to calculate those stresses, or you can draw a Mohr circle to calculate the stresses. Okay, any question, people? You may unmute yourself if you like, if you have any question. I need to do polling. All of you are awfully quiet.
I think I'm just gonna have to work with it a little bit more before I have like an actual question to ask.
Okay, so why don't you guys, I have office hours tomorrow. I also have office hours on Thursday. So why don't you guys work on the practice problems and also homework, right? Homework has 2 problems for Mohr circle, as well as from stress transformation, right? So if you guys have done your homework, I mean, you can also do some practice problem, look at example problem sheet, and if you have any question, you can ask me. And as for the thin cylinder problems, thin walled pressure problem, pressure vessel problems, those are simple. You just have to know which formula to use and where the stresses are. Or if I ask you to, hey, draw a stress element for the longitudinal and circumferential stresses, all you have to draw is the element showing sigma L, sigma C. So those are pretty straightforward. We're gonna look at one problem on Thursday. All right, if you guys do not have any questions, yes, Emily, do you have any question?
Yeah, I have one. It's just kind of off topic. It's about the extra credit homework.
Yeah, go ahead.
I noticed that when you posted the assignments, the problem 3 was missing the answer for it.
Oh, really? Let me see.
Yeah, because I was looking at the question and it asks us to derive the equation of the elastic curve.
Oh, okay, that's because, let Let me pull it out. Give me a minute.
Okay.
Homework 3.
It was the extra credit homework.
Okay, yeah, I got your homework 3 extra credit. Okay, you're talking about problem 6.3, right?
Yes.
And problem 6.3 is, I have to go back to the book. Ebook, chapter 6. Six point three. Okay, the intensity of the distributed load on the cantilever beam varies linearly from 0 to W0. Okay, derive equation for elastic curve. Okay, the reason I didn't put it is, okay, it asks for an equation, so okay, I will give you guys the expression, but I want everybody, those who are submitting extra credit, because it is optional, please make sure you show how you derived it, okay? The procedure, just don't give me the answer. Okay, I'll put it.
Okay.
And remember, for extra credit, I mentioned that, I mean, it is just to bump your grade a little bit at the end. So based on where the class stands, I will choose the percentage being added, okay? For now, most of you have done good in your last midterm, so it looks pretty good. All right, any other question? Everybody, okay, Crystal, and can you just stay back? I wanted to ask you something. Other than that, I will end the class here. Crystal, you submitted the homework 3. You emailed me homework 3. Am I right?
Yeah, I got messed up when I scanned it.
Okay, are you able to submit it through Blackboard now?
Then I can try.
It doesn't get uploaded when you try to upload it?
Give me one moment.
Let me open up your file. Homework 3. So I'm able to open it. Just try and see if you can submit it.
It like has my old one up there, and I don't know how to take it off and then submit.
Oh,
like,
you can resubmit. You don't have to take it off. Resubmit it. I always grade. So you have multiple options. I always give multiple submission attempts, so that if somebody makes a mistake in the first attempt, is able to re-upload the second one. And I always grade the last one uploaded.
Oh, okay. I just couldn't figure out how to do that.
Yeah, you cannot remove it, but you can resubmit another one, and I'm going to grade the last one you submitted. Okay?
Okay, thank you.
All right, everyone. I'm gonna see you all on Thursday. I'm ending the class here.